Good evening, PAD and POS 316ers. This is our short mini lecture covering how to construct confidence intervals and an introduction to hypothesis testing. So we've gone over a lot of different information related to how we can use estimation that comes from samples to make inferences about an entire population. And we've talked about extensively why we need to do this, relating to the difficulty and sometimes the impossibility of getting true data from the entire population. It can be very expensive, it can be impossible, and if poorly done, it can actually give you false results. So in your homework this week for calculating confidence intervals, you are given a situation to think about where you're an analyst that's thinking about using sampling. You've pitched a project where you will be using sampling instead of population data to detect fraud by nonprofit organizations using their tax data. So what you had to do in this example was to really think about some of the assumptions and some of the reasons that we would use inference and that we would use estimation instead of gathering a whole bunch of data from an entire population, which in this case was theoretically possible. In this case, using sampling in inference actually saves a lot of money, and you'll find that in a lot of cases this holds true, especially when you're talking about states or localities where you can have hundreds of thousands or even millions of observations or cases that you would need to look through, and it takes a lot of manpower to do that and a lot of time. And so sampling, inference, and estimation can really give you a good perspective of what's going on in the entire population and allow you to make good decisions. So we've talked a lot about why you would use inference instead of just taking a whole bunch of data from the population. There's a lot of information in the readings and lectures from the past few weeks and also from the Whelan text. So the other thing that we have to think about is that while using inference and estimation instead of population data is generally a very good thing and in some cases is the only practical thing to do, there are also some limitations that are associated with inference. The big one, and this is really not acceptable for a homework answer, is that you are using a sample to represent, or multiple samples to represent an entire population. So when we do that, we introduce problems with bias and variability, which make it so that our estimates, our point estimates to be more precise, are not as exact as we would like them to be. So for that reason, we need to use techniques like using confidence intervals to express our point estimates so that we are being as clear as possible about the limitations of our data, what our data is saying, or what our data is not saying. So there are a lot of issues that are associated with inference that we've talked about, and Whelan gives a lot of really good practical policy-oriented examples, which you can use in your homework. So what we know is that point estimates when we're working with sample data are very precise estimates of things like the mean or the median or the standard deviation or the variance, and that those point estimates are not exact. They're not perfect representations of the population because our samples or our sampling distribution may be representing some bias and some issues with variability that make things a little bit fuzzy. That doesn't mean that these point estimates are useless. It just means that we need to use confidence intervals to express them so that we are being very clear about the range of values that is appropriate to consider when we're talking about point estimates. So we're going from a single point to a range, and that's a good thing. So with that, you're also asked in this homework assignment to talk about proposing a hypothesis that you may want to test. And so, as you remember from our discussions in class, hypotheses are just very specific ways to ask questions about your data. And they can be interesting questions, they can be boring questions, but you have to be very specific about how you are setting up your hypotheses, because you need to be very careful about how certain you are, or expressing how certain you are about the likelihood that your hypothesis, if you say it's true, it's actually true, and your hypothesis, if you say that it's probably not true, is actually probably not true. So the way that we set up hypothesis is we have our null hypothesis, which I'm going to say is HO, and in this case, I'm going to propose a hypothesis about homeless population, or homeless services spending in New York and Florida. So let's say that we take some samples from New York and Florida, and we'd like to compare them. So my null hypothesis is going to be that homeless services spending is the same in New York and Florida. Okay, so based on these samples, I'm going to see if the average spending is the same in New York and Florida. And this can tell me, it can point me in very specific directions for kind of digging into why, if New York and Florida are not the same, that might be, and that could lead to some interesting policy conclusions and some interesting analysis. So that's my null hypothesis. My alternative hypothesis is what happens if I reject my null hypothesis. So I'm going to call that HA. And what that specifically means is we would say homeless services spending is not the same in New York and Florida. Now in class we talked about this very weird thing in science, and especially in the social sciences, where what scientists hope most of all is that they get to reject their null hypothesis, because this is kind of boring. If homeless services spending is the same in New York and Florida, there's really not very far I can go from there. We say, yay, they're the same, that's great. But if I get to reject my null hypothesis in favor of my alternative hypothesis, I get to consider, okay, why is homeless services spending not the same in New York and Florida? Does it have something to do with the population that lives in each state? Does it have something to do with the money that's allocated or the organizations that are operating within the state? There are a lot of different places that I can go with that. So in science, rejecting the null hypothesis is very exciting, and it's a very good thing. If you want to qualify something like that as a good or a bad thing. So after we set up our hypothesis, we do our test. We can run a t-test or an f-test, comparing the means or the dispersion of the data, and we can decide that we're going to reject the null. And scientists say, yay, when this happens. And that just means that we would conclude that homeless services spending is not the same in New York and Florida. So that's what happens when we reject the null. And then we go on and we ask why that is. So the next thing that we might do is we might fail to reject the null. And scientists get very sad here because, I'm going to make that a frowny face, because what that means is that there's really not a lot more to dig into there, and typically you're not going to get published if you're failing to reject your null, which is a bad thing, which leads to publication bias, but that is a total rant for another class. So when we fail to reject the null, what we're doing is we're saying that homeless services spending is the same in New York or Florida, or that we don't have enough evidence specifically to say that homeless services spending is the same, or excuse me, is not the same in New York and Florida. So we just don't have enough evidence at this point with the data to support our alternative hypothesis, so we stay with our null. So after you do your testing and you figure out if you're going to reject the null or fail to reject the null, a couple of things can happen. So you can reject the null and that is the correct thing to do, or you can reject the null correctly, or you can reject the null and what happens there is that it's incorrect and you actually should have stayed with failing to reject the null. Or you can fail to reject the null incorrectly, and you can also, fail to reject the null correctly, or you can fail to reject the null incorrectly. Okay, now these are tied to our considerations of confidence levels, and specifically the value of alpha, the thing that looks like a little fish that we can discern from the confidence levels that we set when we're looking at data. So I'm going to take a step back, and what we're going to do is to actually talk about what's going on right here. Okay, so when we're looking at what happens after you reject the null or fail to reject the null, what we're doing is we're saying these four things can happen. Either we're rejecting the null or failing to reject the null and we're actually right, or we're rejecting the null incorrectly or failing to reject the null incorrectly. And we can link that to our knowledge of type 1 error and type 2 error. So what we have here, if you remember from our previous classes, type 1 error is a false positive, type 2 error is a false negative. So if you think about it, type 1 error being a false positive is what happens when you reject the null incorrectly. You think you found something, but you really have not. Okay? And type 2 error is a false negative, and that's what happens when you are saying, okay, we didn't really find anything in our data, so we're going to stick with our null hypothesis. So you're failing to reject the null incorrectly. Okay, so what we're doing here is what you're saying, what your inference says, is that if you reject the null incorrectly, your conclusion is that homeless services spending is not the same in New York and in Florida. But what is really true, I'm going to make this a little bit bigger, or I'll just adjust this a little bit. Here we go. What is really true is actually that homeless service spending is the same in New York and Florida. Okay, so the next thing is type 2 error, false negative, you failed to reject the null incorrectly. So what you're saying is your inference is telling you that homeless services spending is the same in New York and Florida, but what's really true is that homeless services spending is not the same in New York and Florida. So this is one way to think about what type 1 and type 2 error is with hypothesis testing. The other thing that we need to think about is, okay, well, we know that we have type 1 error and we know that we have type 2 error, but how do we tell how much of it, or what's the likelihood that we have type 1 or type 2 error in our hypothesis testing? So we're going to link this very closely to our confidence levels and our confidence intervals. So you know that when you are constructing confidence intervals, what's actually happening is that you're going through this multi-step process, right? You are choosing a confidence level, right? And typically our confidence levels are 90%, 95%, and 99%. And you are choosing a confidence coefficient, which is just the decimal form of our confidence level, so it would be 0.90. Whoops, let me change that to a number. 0.95, and 0.99. And we're just going to change those to numbers as well. Okay, and then what you do is you calculate alpha, right? So your alpha level is going to be 1 minus the confidence coefficient. Okay, and that would be 0.10, 0.05, and 0.01 in this case. So those are our different values of alphas. And then you divide alpha by 2. You just take alpha divided by 2. So that would just be this divided by 2. We would take this divided by 2, and we would take this divided by 2. Okay, and using our alpha divided by 2, we can go to our tables, our z tables, which I'm going to bring up in just a second. Okay, so we would go to our z table, which is right here, to find our z-score, which we're going to call our step 5. So, for example, let's say that, let me make this a little bit smaller. Oh, that's really annoying. Okay. I'll bring this back down in just a second. Oh my. Okay, so we're making this smaller so that we can look at it. This is also in the back of your textbook. So if we are saying that we want to find these z-scores, what we would do is look at this level of alpha divided by 2, which is actually talking about the area under the curve. Right? So what you have is this area under the curve, and what you want are the z-scores. So step 5 is find the z-scores. Okay, so the first one is 0.05. So what we would do is we'd go into this table and we'd look for the number in the center that is 0.05. And that might take you a little bit of time to find. And we're going to find here that it's between 0.0505 and 0.0495. Okay, and that is negative 1.6. All right, and then for 0.025, if we go and we look for 0.025, that's right here. So that is negative 1.9. Okay, and then our final one is 0.005, so we would go and look for that. And let's see, 0.005, you might be looking for it for a little bit. It's like, where's Waldo in here? Okay, it's going to be right about here, so that'll be negative 2.5. All right, so what we've done is we've identified the confidence level, the confidence coefficient, we've calculated alpha, we found alpha divided by 2, and we found the z-scores, which are all the steps that are related to finding your confidence interval. But we're going to take a step back to talk about what this confidence level and what this alpha level actually mean, okay? So when you are using your confidence levels, what you are saying is specifically that you have a 90% probability of avoiding type 1 error. Okay, another way to say this is that you have a 10% probability of making type 1 error. Okay, and remember, type 1 error is our false positive when we reject the null incorrectly. And this goes the same for 95. So you're increasing the probability that you avoid type 1 error. Now you only have a 5% probability of making a type 1 error if your confidence level is 95%. All right? And then if you have a confidence level of 99%, what you're saying is that you are 99% confident, you have a 99% probability of avoiding type 1 error, or you have a 1% probability of making type 1 error. Okay? So there we go with that. So what we can see here is our alpha level is actually just telling us the probability that we're going to make a type 1 error. And as some of you have asked in class, why the heck would you have a 90% probability of avoiding type 1 error or 95%? Why wouldn't you go with 100%? And the reason for that is that the more you increase your confidence level, the more that you're concerned with avoiding type 1 error, the higher your probability of having type 2 error. So the more that you assure yourself that you will not have type 1 error, the more you increase the probability that you will have type 2 error. And that can actually be a big deal for some research questions. So what we talked about up here was, a situation with spending, which is fairly, let's call it innocuous, right? But let's say that we have a different kind of question where we're talking about sending an innocent man or sending a prisoner to death row. Okay? So our null hypothesis is that, let's say, the prisoner is guilty because we're talking about sending them to death row, right? And our alternative hypothesis is that the prisoner is not guilty. Okay, so working through this problem, working through talking about type 1 and type 1 error and type 2 error, a false positive in this case would be when we actually, our inference is telling us that the prisoner is not guilty, but the prisoner is really guilty. So the outcome that we're talking about here is setting a guilty man free. Okay? Now that might not be such a bad thing in some cases, but what about this other one? What about when we have type 2 error? Okay? And type 2 error in this case is that our inference is telling us that we need to fail to reject the null, right? So we need to say that, okay, indeed the prisoner is guilty, they should go to death row. But what is actually true is that the prisoner is not guilty, and what you're actually doing is sending an innocent man to death row. Okay? So in this case, you might want to make a trade-off where your acceptable level of type 1 error is lower so that you have a lower probability of making a type 2 error when you're sending somebody who is innocent or somebody who is not guilty to die. So this is maybe a different example that would be a little bit more intuitive for some of you to think about. Okay, so we've talked about what the confidence level is actually saying. So in relation to this example, if we set a confidence level of 90%, what we would actually be saying is that what we want to do is have a 90% probability of saying the prisoner is not guilty when in fact they're guilty, okay? Or we would want to say that we have a 95% chance, or if we set it at 95%, what we'd be saying is we want to be 95% sure that the prisoner is indeed not guilty when we have a 5% chance of saying they're not guilty when they really are guilty. So this is something that you can think about and consider. I'm going to upload this spreadsheet along with the mini lecture. So just going back to our calculations of confidence intervals, what I'm actually going to do is to take this and put it on a different sheet. So in order to calculate confidence intervals, we need a few things. We've gone through the steps of this. We need to set a confidence level, which typically is between 90 and 99%. We need to find our confidence coefficient, which is just the decimal form of our confidence level, which is expressed as a percentage. We need to calculate alpha, which is just 1 minus the confidence coefficient, which is right over here. And our alpha tells us what our probability of making a type 1 error is. We need to divide our alpha by 2, and we need to use that in order to find the z-scores in our density tables. And then what we do